We're going to talk today about relative extrema. This is something actually we're going to be talking about for the next few times. So it's sort of a new thing, although you will see the methods that we use to talk about relative extrema are actually the same as the stuff about increasing, decreasing that we've been doing for a couple times now. So it is new, but similar, very similar, at least the techniques, to what we've been doing recently. Relative extrema, what the word refers to is, if I have a function like that, maybe, the relative extrema, they are the points that are sort of at the top of little bumps or at the bottom of little bumps. They're like the mountain peak points or the valley points in a function like this. So in this one that I'm looking at, I can see 4 such points. Those and this one, right? These are called the relative extreme points. And if you want to be more specific, some of them are called relative maximum points and some are relative minimum points. Depending on the y value, relative maximum means that the y value is larger than all of the nearby points, and relative minimum means that the y value is lesser than all of the nearby points. So for example, this one is a relative maximum. It's the reason that I put a dot there is because its y value is greater than the y values of all these points. And this one also is a relative maximum. So this is a relative, actually the plural would be relative maxima. That's the plural of maximum. All right. And then these two are relative minima. And then the word extrema refers to just any of these kinds of values, be they maxima or minima. All right, these are the relative extrema. Why are they important? These are very important in the real world. If you're looking at a function that represents some kind of data, there are many reasons why you would care about such functions. If you're looking at, say, let's say this function represents the value of some investment, say a stock, stock prices, they go up and down all the time. As you know, your goal as an investor is to basically buy low and sell high. If you are capable of knowing when the relative minimum points are and when the relative maximum points are, your investing strategies will do quite well. If this really represents the value of a stock, the relative minimum point would represent a time at which you should buy, right? Because the price right now is as cheap as it's going to be, at least for, it's not as cheap that it is ever, like it was cheaper over here, but at least in the nearby time, at least in the short-term time frame, this is the lowest price you're going to see. So the relative minimum points are the ones where you should buy the stock, and the relative maximum points are the ones where you should sell it, right? You want to buy it at the cheapest price and then sell it at the most expensive price. So a lot of sort of financial forecasting, people trying to make money, their whole game is to try to predict when the relative minimum points will occur and when the relative maximum points will occur. What I want to talk about today is how could you find such points if I just tell you the equation of a function? Obviously, if I show you the picture, you can just point at them. These are the relative maximum points, these are the relative minimum points. But what if you are not shown a picture? What if I just give you the formula for something? Can you tell me where the relative maxima and minimum points are? That's the game for today. And it's not rocket science, really, to notice that the only place that these values can occur is at what we called last time the critical numbers, right? The critical numbers are where the derivative is 0. All of these here have that type of behavior. The derivative is 0 here. That means the tangent slope is horizontal, right? All of these have derivative 0 at them. It's also possible to have a relative extremum when the derivative does not exist, which on a picture would typically look like a pointy point. So something like that, where this just comes to a sharp point right there. This is also a relative maximum because it's larger than all the nearby values. The derivative is not 0 there. There just is no derivative because there is no single tangent line to the curve there. So what I'm trying to say is the relative extrema always occur at the critical numbers. I'm going to write that down. relative extrema always occur at the critical numbers. And the past 2 times we have discussed at length how to find the critical numbers. You take the derivative and you either set it equal to 0 or you say when the derivative does not exist. So we know how to find the critical numbers. This is like you're halfway there to determining what the relative extrema are. Even if you can't see the picture, you can still find the critical numbers. The other question is, once you have the critical numbers, how do you know if they represent a minimum or a maximum? All right, and that you can deduce using the same chart that we saw before. Check it out. If I have a function like this and say here's a critical number here, I will have you notice that the derivatives over here, well, can I just say you don't even have to really think about the derivatives. The function over here is increasing because the y's are going up as you go to the right, followed by decreasing, all right? Whereas a minimum point looks like this, which has decreasing followed by increasing, all right? This is how you can tell, even if you don't see the picture, we already know how to determine if the function is increasing or decreasing in various regions, right? And so, even if you don't see the picture, if you know what the critical number is, and you know, does it go from increasing to decreasing or decreasing to increasing? That's enough to tell you if this is a relative maximum or a minimum, right? If the function goes increasing and then decreasing, then it's a maximum. If it goes decreasing and then increasing, then it's a minimum. So, I'm going to try and summarize all of this. All of these ideas here on finding relative extrema are referred to as the first derivative test. It is a test using the derivative because you are seeing if it's increasing or decreasing. Using the derivative to determine if certain points are relative maximum or minimum. I'm going to write down in detail and then we'll do an example. All right, this is the first derivative test. I'm going to write it as a theorem. Theorem is just like a fancy word for a true fact that you can prove mathematically. We're not going to prove it. I think it's actually kind of obvious if you think about it in the proper way. First of all, the relative extrema always occur at the critical numbers. And if f prime goes from positive to negative, that means the graph is going up and then down again. At that point, then your point was at the top of the hill, and so it is a relative maximum. If f prime goes from negative to positive, that means it was going down and then back up. Then your point is at the bottom of the hill, and so it is a relative minimum. And otherwise, so this is technically possible, although it doesn't happen very often. It is possible to be positive and then positive again. That means it goes up and then levels out, but then it goes up again. Then that point is not a maximum or a minimum. It's just sort of in the middle of a weird level out, but then it goes up again. So if it's positive to positive or negative to negative, then it is neither, not a relative maximum or a minimum. All right, this is called the first derivative test. A typical, homework problem or something would give you a function and say, use the first derivative test to find all the relative minimum or maximum points. So let's do one. All right, let's find and identify all relative extrema for this function here. So the identify refers to, so find means tell me what the x values are, and then identify means for each of those, tell me if it's a maximum or a minimum. All right, this is what we got to do. Now, the procedure here is actually pretty much the same as the whole increasing decreasing business. The only difference is really just how you interpret what the chart says at the very end. So we're going to begin like we did the increasing decreasing thing, which is first take the derivative in order to find the critical number. So the derivative, I just go down here. This is an easy derivative, 6x squared minus 6x minus 72. Can you believe it? 72. And then I want to simplify this as much as possible. I guess I could factor 6 out of everything. X squared minus x minus 12, right? And then this guy I can also factor 6, and then here I'm going to do, looks like x minus 4, x plus 3. All right, this is as good as this is going to get. The derivative is 6 times x minus 4 times x plus 3. Okay, what are the critical numbers? I got to set this equal to 0 and solve for x. F prime of x equals 0. What does that say? 6 times x minus 4 times x plus 3 equals 0. It's already factored for you. This 6 doesn't matter at all. I can just divide by 6 on both sides, and this will go away because 0 divided by 6 is 0. So just throw away the 6 to get started. And then I split it up. Those were the factors, and then we split it up. X minus 4 equals 0. X plus 3 equals 0. I get x equal 4. X equal minus 3. These are my critical numbers. Remember, we also must check when the derivative does not exist. But in this example, the derivative is just a polynomial, right? There's no denominator or anything, so the derivative does always exist in this case. These are the only critical numbers. All right, now we're going to make a chart with the critical numbers labeled, and then plug a bunch of stuff into the derivative. Let's do it. All right, I have made my chart here. This is the derivative. These are my critical numbers, -3 and 4. And now, like before, when we did the increasing, decreasing thing, I'm going to plug some values in to determine the signs of f prime. So to the left of -3, my favorite number less than -3, I suppose, is -4. So I'm going to go f prime of -4. And then I plug in to the derivative. So it is 6 times -4 minus 4 times -4 plus 3. What is this? In terms of positives and negatives, this is positive, the 6. Here is -8, so that's a negative. And then here is -1, that's another negative. The answer is positive, right? So right here, the derivative is positive. Okay, how about in the middle, between -3 and 4, let's use 0. You know me and 0. 0 minus 4 is -4. 0 plus 3 is 3. What do I got here? A positive, a negative, and a positive. This is a positive times a negative times a positive, which is negative. And so it's negative in there. And then finally, to the right of the 4, let's choose 5. 6 times 5 minus 4. 4 plus 3. This is positive, positive, positive. It is positive, positive. All right? Positive. This is the chart, just like so far. Actually, we've done no different from what we would have done if the question was just, is it tell me where is it increasing or decreasing. Here's the only difference is how you interpret this chart. How do you check out this chart? Remember, our job here is to find the relative extremum and say for each one, is it a maximum or minimum? The first derivative test says the relative extrema occur at the critical numbers. So these ones are the numbers which we should say in the answer. So I'm going to say x equal -3 is a relative, fill in the blank here. You got to tell me, is it a relative maximum or minimum? And the way you tell, according to the first derivative test, is if the derivative goes from positive to negative, then it's a maximum. Positive to negative means it's going up and then starts going down. So that point is at the top of the hill. If it's going from negative to positive, then it's a minimum. That's what the first derivative test says. So what is it for this one? X equal 3 is a relative. You look here, it goes positive and then negative. That means it goes up and down. So -3 is at the top. So it is a relative maximum. All right. How about that one? X equal 4 is a relative. Look at the signs. This one goes down and then up, which means this is a minimum. All right, that's how we do it. As always, you can graph this on your calculator or on a computer. You should notice on such a picture, hopefully, if you did it right, you will see x equal -3 is like a top of the hill point. That's what relative maximum means. And x equal 4 is the bottom of the hill. I think we got it.